Hello guys, we are here to discuss a very key topic in chemistry. If you are already a subscriber, thanks for coming back again. And if you are new here, try to click on the subscribe button and also on the notification bell and endeavor to like and share our video and give a good comment. Thank you. So we want to talk about the particulate nature of matter. So we all know what matter is. Matter is anything that has mass and occupies space. So matter exists within the earth and in the space. So and we believe that all these matters interact with each other, and apart from that, that is what physics is all about. So but in chemistry, you could be scientists were in those days like were curious about what every matter could be made up. So and then there are certain things that are associated with matter, that is basically the changes that they undergo. So and the changes could be physical and it could be chemical changes. So but chemical changes has a kind of not a physical explanation to tell how it happened or why it happened, but physical changes have like a physical explanation on how it happened or why it happened. Take for instance, if you melt an ice cube, so it's a physical change because you can reverse the process. You can at the same time put the water formed from melting the ice cube into a refrigerator and allow it to freeze again, or when it freezes again you can bring it out so it will melt. So we know what could cause that. Like we know in terms of thermodynamics, we know that the process is spontaneous, and the ice is getting heat from the surroundings to melt itself. So we know that it's melting, freezing, or let's say you dissolve a common salt, that is sodium chloride, in water, and you try to separate it by evaporation to dryness. So that shows their physical changes. However, we have chemical changes that could not be explained by physical means. So then this makes scientists curious about what is inside the so-called matter. So and then matter extends from solid, liquid, and gas. So anything around you, being it powder form, it's a solid, and we have the liquid and we have the gaseous state. So now we were able to and the early scientists were able to discover a smallest particle. In the days of John Dalton, the smallest particle that could be present in matter was described to be atom. So and it was a divine atom as the smallest and indivisible. Sorry, we are talking about particulate nature of matter. So and that is a topic in chemistry. Okay, well, we also have the same topic in physics, but however, the way we treat it here will be different from the way we treat it in physics. So, as I was saying, we have these, and John Dalton gave his own theory about atom, because he gave those theory which was later remodified, or let's say modified, by the new discoveries that are made that render those theory, let's say, not properly functioning well as the new discovery. So one of those theory was that atom is not divisible. It's the smallest and indivisible particle of an element. Now, when we say matter, matter is made up of elements. Yeah, if you see a big, let's say, car in your present, so the car is made from some materials like iron. Maybe the engine is made from a kind of iron, maybe cast iron or whatsoever. So the iron is a material which happens to be an element. So in every element we have many elements, about 100 plus elements. So and then each of them have atoms, and the atoms of each element are different from one another. So but let's take it down to the atomic level and talk about what atom is. Dalton described atom as not being divisible, and he also said that all these chemical changes we're curious about how they happen. They occur as a result of rearrangement of atom or combination of two or more atoms. So that was his like there were more theories he gave. Like he said, atom can neither be created nor destroyed. You cannot create an atom and you cannot destroy it, being the smallest. And then he also made mention that all atoms of the same element looks alike and the same in all ramification. Are you getting it now? So those are the theories he made, but discoveries has made these theories, let's make it valid, and then it has been modified. So because varieties of discovery has made that not really on a good stance. So now, apart from atom, we need to talk about the structure of atom, because now we have discovered that atom could be is not actually the smallest, and it contains of three more subparticles. So every atom consists of three more subparticles, which is proton, neutron, and electron. And the positions or the structure of atom shows that there is a center or core, which is like a very dense center, and it's where the mass of the atom comes from. So then around it you have a shell. Are you getting it now? So you call it energy level. So the electrons around the shell is not just like they maintain an orbit just like a planet moves around the sun. No. So they are just there in terms of they move around in their orbitals. Like orbitals are the likely position they could be found. You cannot give exactly their position and their momentum. So, but they exist like a circular standing wave around the nucleus. So this point is called the nucleus, and it consists of proton plus neutron. And that is where the mass of the atom comes from. So that indicates that proton and neutron are the only particles that are massive in atom. Meanwhile, electron has a very negligible mass. So it's when your mass is smaller, that means you're going to have the tendency to move around because you have a small mass. And then, okay, let's leave that for physics. So now this is electron, and this is shell, which could be called energy level. So, however, we have a lot of things associated with this, which we want us to talk about in atom. So now we have remodified the definition of atom to be the smallest particle of an element which take part in chemical reaction. So unlike Dalton's atomic theory that says that it is indivisible, now we can see that it contains three more subparticles, so it is divisible. Then another thing is he said that all chemical changes result from rearrangement of atoms and all that. So but now we have discovered that it is not actually the rearrangement of atom that leads to chemical reaction. It is the behavior of the proton and electron that brings about chemical reactions. So not actually the atom itself, it is the component of the atom that give rise to those chemical changes. So then we define atom as a particle that take part in chemical reaction, but not directly actually the one responsible for the changes. So now that is the atomic level. However, when we say energy level, we call it energy level because the positions of electrons around atom has a particular energy associated with it. So the energy could be represented by the Max Planck equation, Hf, which is Planck's constant, multiplied by the frequency of their motion. So we are not going into this. So now, the closer shell to the nucleus is called the ground state. So where you have zero or no or minimum amount of energy. So now there are other shells you could choose from. So then, which means when energy is supplied to atom, they could jump from their initial shell to another shell. So that is why they call them energy levels. So depending on the amount of energy an electron possess, that is when we're going to talk about the shell is going to be present. However, what makes the difference between atoms to atoms, like atom of iron to sodium and various elements like that? So what makes the difference is just the number of proton, and the number of proton controls the number of electron. So take for instance, in the nucleus you have one proton, that is the smallest atom. So the smallest atom will just have one proton, and that is hydrogen. So this number of proton is also called atomic number, and it must be equal to the number of electron outside the nucleus. So if you have one proton in the nucleus, you must have one electron outside the nucleus. So we're coming back to number of neutrons. So which means the number of proton and electron must equalize for an atom to be neutral. So the charge on proton, when you say proton, the mass is always 1, and the charge, that is for mass, and the charge on proton is +1. So then electron, let's say, has no mass or very negligible mass. So electron has the mass of 1/1840. So that is a very small mass, so it could be neglected. So then the charge is going to be what? -1. So which means if you have 1 proton, the charge in the nucleus is +1. So there must be 1 electron outside the nucleus to make the whole atom 0 charge. Okay, so now all atoms have a charge of 0. Now, if you tamper with the electrons outside the nucleus, it leads to the formation of ions, because now, as I've said earlier, the number of protons must be equal to the number of electrons. So now, if proton is in the nucleus, it does not move. So which means the number of proton cannot be affected by chemical reaction. Only the number of electrons can change and brings about chemical reaction. So I'm not talking about nuclear reactions. Nuclear reactions are associated with the nucleus, and then proton could be destroyed or evolved from the nucleus. No, we're just talking about the normal chemical reaction. So as I was saying, now when electron is being removed from such atom, don't forget the atom is actually neutral. Let's take for instance sodium. Sodium has 11 proton and 11 electron around the nucleus. Good. So now, if sodium, now the total charge in sodium atom Na is 0. Now, if sodium loses an electron, let's say you tamper with the electron and the electron was removed, so then what happens? The number of proton will be automatically more than the number of electron by 1. Yeah, so because you'll be having +11 and then -10, so which means if you add that together, the +11, then you have -10. So if you add that together, you'll be getting +1. So then this will be sodium ion. So now, for the case of chlorine, chlorine has a 17 proton and then 17 electron. If this is the case, having 17 proton, 17 electron, in the case that you are neutral. So then, for the case of chlorine, chlorine only accepts electrons. So accepting that electron will make the number of electron in chlorine be 18, while this will be 17. So the overall charge will now be Cl-, making it an ion. So we understand the difference between atoms and ion. So the movement of electron out of an atom and into an atom forms an ion. So meanwhile, an atom have to be neutral. Now, how do we differentiate from atoms from each other? It is based on their atomic number, which is the number of proton. The number of proton is also called atomic number. So now, if I have 1 proton, that describes that I'm hydrogen, and no other atoms of element could have 1 electron in the nucleus. So now, the atom becomes more heavier and complex as the number of proton in the nucleus increase. So that gives a difference. And when you were learning the first 30 elements, right, from hydrogen to zinc, so the number of the number of proton in their nucleus increase in order of the arrangement. So which means hydrogen, helium, lithium, beryllium. So that's in accordance the way the number of proton increases. So they arrange them according to atomic number, which is called the number of proton. So in that case, we have that. So the number of proton are present in the nucleus is called atomic number. Now let's come back to talk about neutron. Neutron has nothing to contribute other than mass. It does not contribute any charge to the atom. So it has a 0 charge. So now, the number of neutrons could vary in atom. So we used to believe that the number of proton must be equal to the number of neutron. No, because we have the case of some atoms that have the number of proton. Let's take for instance, we have sodium, the number of proton is 11, and then the number of neutron is 12. So that makes the mass of sodium to be 23. Don't forget I told you that the mass of an atom is contributed by just proton and neutron. So having discussed these, we understand the concept of what atom is, and we break it down so as the particle in every matter. So now I make mention of proton and neutron together in the nucleus, but electron has a specific arrangement outside the nucleus. So, and don't forget I told you that you have energy levels or shells. So that shows that the electrons that are outside the nucleus cannot have the same amount of energy. So that means they will maintain different positions in atom, especially the complex atom that has more than 1, 2, 3 electrons in their outer shells. So now, which means we're going to talk about the electronic distribution of atom. That's which we can call electronic configuration. So now, what is the electronic configuration of atom, or you call it electronic distribution of atom? So as I was saying, the number of proton and the number of electron must be equal for a neutral atom. So now, the number of proton and neutron are in the nucleus packed together, meanwhile electron is outside the nucleus with a specific arrangement. So in that wise, we want to talk about what's arrangement, how are they arranged from the simpler atom to the more complex and more complex atom. So the complexity of the atom is now the number of proton. I think I told you the increase in number of protons, so which cause increase in number of electrons since they have to be equal, and then you talk about the arrangement of electron. So now we have a shell, the first shell closer to the nucleus. We have other shells, and it continues like that till infinity. So, and each shell has a particular energy associated with it, so we call it energy level. So we can assign a given number to those shells, so that is 1, 2, 3, you can give them a number and so on. So, and then you can assign a letter to them, which was K, L, M, like that, O, P, like that. So it does not have a hand. So this number we assign to each shell is called the principal quantum number. And the word quantum has to do with particles, small particles. So when you hear the word quantum, it means small particle. So this is the principal quantum number. The principal quantum number corresponds to the number of shell or energy level in an atom. So for example, an atom can just be making use of just 2 principal quantum number. Some can just make use of 3 principal quantum number. So this is the principal quantum number. So if I say that an atom is making use of 3 principal quantum number, that means it's making use of 3 shells, which means 3 shells in that atom, electrons are there, if not full completely. It's because the first shell have to be full before you move to the second shell, and the second shell have to be full before you move to the third shell. So now getting to the third shell, and you said an atom uses the 3 principal quantum number, so which means the first shell could be full and it may not be full. So which means we have different atoms that may be using 3 principal quantum number. So now there is an available space in each quantum number. So we said the principal quantum number corresponds to, okay, let me just write it. Principal quantum number corresponds to the number of shell or energy level, so which range from 1, 2, 3, 4, 5, like that. So, and as I was saying, I said this principal quantum number has energy associated with it. So, and then apart from that, there is a particular space that is available within them. So the space available in each of them, just like in a house and in a sitting room, let's describe as a sitting room, there could be available chairs. So, and the type of chair will determine how many people will be able to sit in the sitting room. Now, In the first shell, there is no enough space. So the only available space can only take 2 electrons. And that available space is a type of orbital called s orbital. So which means we have the first number, which is called the principal quantum number, that describes how electron is arranged. Then the second one is the space within the principal quantum number, the space between them. So that space between them is called subshell, and we give them letters like S, P, D, F. So we call them the subsidiary or ZIMO quantum number. So we call them the ZIMO quantum number. So you can also call them subsidiary quantum number, and we have a letter to represent them, that is S, P, D, F. So these are the subsidiary or the ZIMO quantum number. So and then there is available space in them, so which means for S, the space in them is what we call, you can also call them orbital, directly or indirectly, they are orbitals. So we have a S orbital. So the orbital is just 1. Okay, let me just put it, orbital, and number of electron. So this is orbital and number of electron. So this subsidiary quantum number S has just 1 orbital. And the 1 orbital, let's describe it like something like this. So it could only take 2 electrons. So the P has 3 orbitals, which could take 6 electrons. We have D as 5 orbital, which could take 10 electrons. And we have F, which is 7 orbital, which could take 7 electron, 14 electron rather. So the number of electron are fixed into the orbital like this. However, in every principal quantum number, like every energy level, the number of subsidiary that could be in it will determine how many electrons it could take. Take for instance, the first shell only contains s orbital. The first shell only contains s orbital, so which means it could only take 2 electrons. So that signifies that 2 electrons can only enter the first shell. Then every other shell, using the octet rule, we assume that they could have 8 electrons. So every other shell should take 8 electrons. So which means, looking at it, if you want to write for hydrogen, the configuration, you can use the SPDF notation. And we have other quantum numbers that helps us write the configuration of SPDF. So we have the magnetic quantum number, that is the third magnetic quantum number. This magnetic quantum number is the quantum number that describes the number of available orbitals in an atom, in the subsidiary. So and it could range from -2 to +2. Okay, -1 to +1, -1, 0, 1, -1, 0, and 1. So that is the magnetic quantum number. It describes how many shells, how many orbitals could be in each subsidiary. Then we have the spin quantum number. The spin quantum number. It is the spin quantum number that tells the number of electrons that will be in each orbital. So that is what spin quantum number is. So now, writing the configuration, we have hydrogen. Hydrogen has 1 proton, so definitely 1 electron. So the configuration, that means it's going to be using the first shell. Then, and in the first shell, you only have s orbital filled with 1 electron. So this is it. Helium is using the first shell as well. So because you have to build on those shells, just like we have rules that governs that. So we have the Pauli exclusion principle. We have the Pauli exclusion principle. We have Hund's rule. We have Hund's rule, and we have Aufbau's principle. Aufbau's principle. So all these rules guide the writing of electronic configuration. So, but I don't want to write it the XPDF notation, so we can make another video on this if you want. So, but let's just restrict ourselves to hydrogen has 1 electron in the first shell, helium has 2 electrons in the first shell, so the first shell is actually complete. So if you're going to the next element, the atom of that element, we now use the next shell. So this is helium, lithium is going to be 2, 1. So this one we are writing 1, we have to continue to other elements. So this would be complete 8 before we could move to another one. So let me quickly speed it up to neon. Neon, we have 2, 8. So which means this shell is complete. So going back to sodium, we are going to be having Na2, 8, 1. You see, every other shell we take 8, 8, 8. So now, sodium is actually using 3 principal quantum number, and the last one, which is the third shell, is just containing 1 electron. So the outer part, like out of the 3 shells, the one that is outer is called the outermost shell. It's called the outermost shell. So now, this is the outermost shell. Good. The number of electrons in the outermost shell here is 1. So if you go to magnesium, the number of electrons in the outermost shell will be 2. So the number of electrons in the outermost shell of neon here is 8, because this is the outermost shell. That of lithium, the number of electrons in outermost shell is 1. Now, look at lithium and sodium. They have the same number of electrons in outermost shell, so they will behave in the same manner, even if they are not making use of the same number of shell. But the outermost shell of this is the second shell containing 1 electron. The outermost shell of this is the third shell and is 1 electron. So that property will just make them behave the same, just that sodium will be bigger than lithium in size. So now we understand the electronic configuration. So in case I would use it in my next explanation, you will have to get it very well. So now let's get rid of this. You can read more on electronic configuration. So that is going to take me to what we call molecules. Molecules are bigger than atoms. One thing about atom is that they cannot stand alone. So they have to combine with atoms of the same elements or different elements. Why? Reason is that atoms cannot stand alone, because the aim of every atom, the satisfaction of every atom, is to make sure that their outermost shell, don't forget we finished discussing what outermost shell is, the outermost shell must meet up with the required configuration. So if the first shell is the outermost shell in atom, it must complete 2 electrons. If every other shell is second shell is the outermost shell of an atom, it must complete 8 electrons, and the other ones must also complete 8. So take for instance sodium, Na, has the configuration of 2, 8, 1. This will make sodium very reactive, and it could not stand alone, so it has to react with other atoms in order to be stable. Why? Because the stability is from the number of electrons in the outermost shell. Neon is very, very stable and is not going to react at all because the outermost shell is complete 8. Helium is not going to react at all because it has only single shell, and the only single shell is having a complete electron of 2, which we call duplet configuration. So the ones that are watching, that are looking forward to get the outermost shell to complete 8 are trying to complete octet configuration. So in that wise, this will be inactive, this will be inactive, because they've gotten what they want and they could stand alone as an atom. But those that the number of electrons in outermost shell has not meet up with the required configuration, either duplets. Take for instance hydrogen. Hydrogen just have 1 electron in the single shell. So and the single shell, the first shell, which is the single shell, contains must have 2 electrons to be stable. So which means hydrogen will still undergo reaction in order to meet up with this configuration. So and then the same thing is happening to other ones that are looking for configuration of 8 in their outermost shell and they are yet to get it, so they have to go into chemical reactions to make sure that they achieve this. Now, in going into chemical reaction, now you are combining two atoms together. Maybe sodium is actually combining with another atom from different elements in order to be stable and then to have an octet configuration. So by doing that, they already form something called a molecule, which is bigger than the actual atom, because atoms comes together to form molecules and they can be 2 or more atoms. So now we now define molecule as the smallest particle of a substance, because when they combine they form substance and they don't longer belong to the atom they come from. If two atoms combine, they no longer belong to the atom they come from. They now form a new thing different from what they are, so which we call molecule, and that will exist alone. And that molecule is present in every substance. So like we have water molecule, we have the molecule of plastics and all that. So each molecule are made from atoms combining together. Are you getting it now? So that is the definition of a molecule. So now we now have varieties of configuration, which brings about different kind of ways atom bonds together. So that will take us to what we call bonding. That will take us to bonding. Good. So bonding is just like let's put it atomic bond, because the reason why we have to call it atomic bond is because when molecules are formed by atom combining. So when atom combine, they form molecules. However, molecule existing alone doesn't mean that molecule you have to see them separately, like you can identify the molecule of every substance. No. So the molecules are also very, very small. So they need to mix together with other molecules to form substance, just like you have water. So water is a substance. However, the smallest particle in it is molecule. So this molecule is formed by the combination of atoms like hydrogen and oxygen to form water. So now this molecule also have force that binds them together, that make us not to see them separately. And this force is called the intermolecular force, which we are going to discuss in another video, or I think I've made a video on that before. So now we have just the bond that involves atoms under this atomic bond. And the three type of bond could be ionic bond, which you call ionic bond. You can also call it electrovalent bond. Then we have covalent bond or covalent bond, and you have a dative bond. So these are the three. Okay, then we have the metallic bond. Metallic bond. This metallic bond exists between metals, like maybe sodium to sodium in metals. So we might not really touch it much. We just want to discuss these three basic ones, like the three basic bonds between atoms. So now, don't forget that this bond is a result of the configuration of atoms. So the outermost shell of atom, the number of electrons there, if it does not meet up with the required configuration, the atom is likely to undergo a reaction. So when they undergo this reaction, we have different kind of bond they form in order to form that molecule. So ionic bond, covalent bond, and dative bond are examples of those atomic bonds. So now, for an atom to be able to participate in ionic bond, there is a type of configuration you must have. So metals are mostly the participants, the chief participants in ionic bond. Non-metals are the second participant, because just like bonding could not take place if two atoms are not ready. So now, what are the characteristics of metal from their electronic configuration? A metal, we have the outermost shell of electron to be 1, 2, or 3. Are you getting that? So a metal, any atom having the outermost shell to be 1, 2, or 3 electrons present. Take for instance sodium. I make use of sodium. potassium is 2881. So which means in the outermost shell, okay, magnesium is 282, aluminum is 283. So if you check this outermost shell, you always find 1, 2, or 3 electrons. That describes such atom is from a metal. There is an exceptional case for hydrogen. Hydrogen has, is making use of the first shell and it has just 1 electron there, but hydrogen does not exist as a metal. Why? Because it behaves like those that have 7 electrons, like chlorine, 2, 8, 7. Don't forget that this outermost shell of chlorine is about to complete 8, so and it needs 1 more electron. Then hydrogen is using the first shell, which can only take 2 electrons, and it contains 1 electron there. So which means it's ready to complete by 1 electron. So this is ready to complete by 1 electron. This is ready to complete by 1 electron. So they behave similar. So that does not make hydrogen a metal. However, it behaves sometimes like them, but it behaves more like the elements that have 7 electrons in their outermost shell. Good. So now we are going to evict hydrogen from ionic bond. Sometimes hydrogen form ionic bond with some metals which we call hydride. Hydride of like metals like NaH. This is sodium hydride. So this is also possible. So that is when hydrogen takes a valency of -1. Good. So now metals used to have 1 electron, 2 or 3 electrons in the outermost shell. That is how to describe them. So the non-metals that are the second partaker in ionic bond, they will have 7 electrons in the outermost shell, or they will have 6 in order to participate in the ionic bond. So because ionic bond has to do with donation of electron, accepting of electron. Then don't forget I told you that donating electron, like removing of electron from atom and adding electron to atoms, are the main thing that cause chemical reactions. So in that sense, the metals, they are ready to lose electron, to donate rather, in order to bond. Now, why do they have to donate? Because the amount of energy they need to donate electron is smaller than the amount of electron they need to accept electron. Why? You have 1 electron in the outermost shell and you need 7 more electrons. So would you prefer to lose 1 electron to bond in order to meet up with your configuration, or you would prefer to accept 7 electrons to bond? So which means the energy required to lose 1 electron by this atom is lower than the energy required to accept 7 electrons. So they will prefer losing electron. So that is why when they lose electron, what happens to their charge from the beginning of the class? It becomes positive ion. So which means they are electropositive. Now, those that are ready to accept electron, take for instance like chlorine, 287. Now, the energy required to accept just 1 electron from maybe sodium and get bonded is lower than the energy required to lose 7 electrons. So it will definitely accept electron and then bonding will take place. So which means I will make use of sodium as an example to explain ionic bond. So you need to know when they write a compound Al2O3, take for instance, you should know that the bond existing in this compound is ionic bond, because aluminum undergoes ionic and oxygen can also accept electron. So you must know that from the basis of the electronic configuration. So now sodium in that sense will lose electron, writing like this, it becomes an ion. Then chlorine is ready to accept the electron, just 1 electron, and becomes Cl minus. So then these two will now have an electrostatic force of attraction, positive attracting negative, to form a compound NaCl. So in this bond now you have ionic bond, and then sodium and chlorine are together stable in such bond because they already share the electron and meet up with their octet configuration. So that is how atomic ionic bond takes place. Then we have covalent bond and dative bond. They are the same thing. But this is a special case of covalent bond, which you can call coordinate covalent bond. Now, covalent bond does not involve donating and accepting of electron. It involves sharing of electron. So just like I needed, take for instance, I'm going to use chlorine as an example. Our outermost shell of chlorine has 7 electrons, so I'm only concerned about the outermost shell now. Good, that's 7 electrons. Then another chlorine atom has 7 electrons as well. So these two atoms can bond together to form Cl2. Don't forget, this is not ready to lose electron. This is not ready to lose electron. So, and if they bond, the bond cannot be ionic. It has to be covalent, because this we have to contribute one pair, one of the pair, and this contributes one of the pair. So they come together and form this. So now they will be stable. Now if you count the electrons here, it will be 8. If you count the electron here, it will be 8. So this type of bond is covalent. It involves the sharing of electron pair that is contributed by the two atoms involved. So the only difference between covalent and dative bond is that in dative bond, it is one atom that contributes all the required pair, while the other just came to bond without any contribution. So example of that is the bond between ammonia bond with 3 hydrogen on a normal pace. Then there is a lone pair here. Okay, let me use a dot to represent the bond between ammonia and hydrogen. Okay, excuse me, let me make use of another marker. So this is a bond between hydrogen and ammonia. So the same bond is represented by that line. Then you have the electrons of hydrogen are the one represented by cross. So this type of bond is covalent. They share electron pair. But this is called bond pair because the electrons come from 2 different atoms. This one will be called lone pair. Lone pair because it's from the same atom and they're pairing. So now this pair, hydrogen ion from nowhere can just attach to it. You know, hydrogen ion means it has lose 1 electron, and then losing 1 electron shows that there is no electron in hydrogen again because it has 1. So now it can just come and attach to it without contributing to the pair, just attach to it and form NH4+. But the charge on hydrogen will still appear there. So this is ammonium ion. So the type of bond that takes place between this hydrogen ion and the lone pair in ammonia is a dative bond because ammonia is the only one that contributes the pair of electron. So with all this, I think I was able to link electronic configuration with bonding for better understanding. Thanks for watching and share the video. Don't forget to subscribe. Thank you.